gonna stop me from learning physics.
I appreciate that attitude.
Okay.
It's Chris.
How are you guys doing today?
You gonna listen to you, brother.
Hooray!
I'm gonna go home. Me too. I'm gonna go back home.
Alright. Last time we ended lecture kind of after setting up a question, so we're going to resume there, looking again at what would happen in an elastic car crash. Any questions, comments, concerns, etc. from you guys before we resume that? Alright. Laptop's acting up. All right. So, on Wednesday we started talking about the difference between collision types. Namely, in an inelastic collision, kinetic energy is not conserved, meaning you cannot rely on it to try to figure out, final speeds after collision. But in an elastic collision, kinetic energy is conserved because the objects involved in an elastic collision are elastic and are able to store the energy as EPE before releasing it back as KE. So elastic collisions on the whole tend to be faster and more chaotic because objects will ricochet off from each other. And this is specifically why cars are designed, heaven forbid you have a car crash, but if a vehicle is involved in a crash, it's designed to collide inelastically. Bumpers are made out of non-elastic materials like plastic and metal to absorb the impact and not spring off of each other. And we began examining the hypothetical car crash as if it were elastic to demonstrate why that is a bad idea. So the two vehicles that we are looking at are a sports car and a truck, self-driving, very fast at each other. And since this is an elastic collision, we cannot guarantee either of their final velocities because we don't know exactly how fast either of them are going to ricochet away from each other, nor even in what direction that will take place. So by examining conservation of momentum, we could figure out the total momentum in the system initially, but we have two unknowns because we don't know either final speed, so we have to consult a second equation to find that has the same two unknowns in it. Now in an elastic collision, kinetic energy is maintained like momentum is, which means we could set up conservation of kinetic energy in much the same way. And this equation would have the same two unknowns in it since the kinetic energy formula has the same variables in it. Rho equals mv, ke equals 1/2 times mv squared. So you can set this up and follow it through, and it would have the same two unknowns in it, and therefore we'd have a second equation with the same two unknowns. The only problem with this method is that the ke formula squares the velocity, and that means that if we try to solve this for one of those velocities, we end up with a very annoying square root. So that's kind of a pain. It works, but it's a pain. And so the method that I recommend is using this third equation as your second equation with the same two unknowns in it. This equation is derived from the conservation of kinetic energy, so this equation only works in an elastic collision. You cannot try to use this in an inelastic collision. But what this equation says is that in a one-dimensional elastic collision between two objects specifically, which is exactly what we're doing here, that the difference between the two objects' initial speeds will also be the difference between their final speeds, but note that they kind of switch orientations from one side to the other. It's very specifically V1 initial minus V2 initial equals V2 final minus V1 final. This is a very handy formula that some very smart people derived from the one above it. And using that formula is a little bit simpler, in my opinion, as our second equation with the same two unknowns in it, because there's no squared that you have to deal with. So this equation is my gift to you. You may use this in place of conservation of kinetic energy because it's usually easier, it's usually simpler. If we use this one instead of conservation of kinetic energy, conservation of kinetic energy would give us something like this if we try to solve for the velocity final of the car, which again would be a bit of a headache if we plug it back into the momentum formula because of the square root and the squared. Instead, if we use that third equation, which is already on your formula sheet, we get something like this. We have to decide which vehicle is vehicle 1 versus which one is vehicle 2. So I've decided that car is 1 and truck is 2. So V1 initial is the 45 meters per second of the car, minus the V2 initial of the truck. Note that the truck is driving in the opposite direction. So we're going to put in a negative number, which is then being subtracted. So that's basically going to end up as 45 plus 45. And then on the right side, we have V2F minus V1F. So that's going to be VF truck minus VF car. They kind of switched positions. You have to note that. If you don't do that, the formula stops working. And this is, again, in my opinion, more straightforward to use in the kinetic energy one. Nothing's squared anymore. It's just the two variables subtracted against each other, which is more similar to what we're dealing with over here on the momentum side of things. This is the momentum formula that we left set up from last time. So we technically have 3 equations and 2 unknowns, and in that case you just kind of have to pick which 2 of the 3 you want to use. I usually prefer momentum and the third one. Any questions before we apply this third equation? All right. To use this third equation, we're going to have to simplify it to be one of the velocities equals something. I'm going to choose to solve it for VF truck, because that will let us add VF car to the other side, get rid of the negative sign. Yes?
I forgot. What is the 72,000 again?
This?
Yeah.
This is the total momentum initial.
Okay.
So for both objects initially, so the sum of their initial momenta, we've got mass of car times the car's initial velocity plus mass of truck times its initial velocity. So each of their separate momenta added together. And the reason it's negative just means that the net momentum of the system points left. And that's because the truck is bringing more leftward momentum than the car is bringing rightward momentum. So the car's momenta is positive 18,000. The truck's momentum is negative 90,000 just because it's pointing left instead of right. And that adds up to the negative 72,000. Does that answer the question? Okay. The fact that the system's momenta points left means that it is favoring the truck, and that is going to be bad news for the car, as we will determine here in a minute. Now again, so that's our left side here solved. Problem is that on the right side, we don't know either final velocity, and that's where the 2 unknowns thing comes in. So we're going to use this equation as our second equation with 2 unknowns. I'm going to simplify it just a line to try to get it into the form of VF truck equals something. The left side is going to simplify down to just positive 90. 45 minus negative 45 is basically just 45 plus 45. So 90. And to get VF truck equals, I'm going to add VF car over to the other side. I like that because it just gets rid of the negative sign. So 90 plus VF car is VF truck. So same equation, just rearranged. And now we've got something that we can write instead of VF truck. Questions, concerns, emotions? All right, so we can bring that back over here. Instead of VF truck, we're gonna write 90 plus VF car. So 400 times VF car remains unchanged. Then we get plus 2,000 times, instead of VF truck, it's going to be 90 plus VF car. Yes?
And the, oh, just kidding. Sorry.
It's okay. If you're unsure of anything, I'd rather you ask than not. But doing this, we've got one unknown. It's in two places, but it's not as bad as if we used the kinetic energy one that had a square and a square root in it, thankfully, in my opinion. So we just have to simplify this to try to get VF car equals number. So 400 times VF car plus, I'm going to distribute the 2,000 in. So 2,000 times 90 is 18,000. Is that right?
Mm-hmm.
Or is it 18?
It's 180.
Thank you. Yep, just checked that. Thank you very much. 180,000 plus 2,000 VF car. Running a little light on space, so I'm going to continue my math over here. I'm going to keep the two VF car terms on the right side, but I'm going to bring the 180,000 over to the left. That does mean we have to subtract it, and that's going to be, the left side is now going to be negative 72,000 minus 180,000, and that's going to be equal to 400 VF car plus 2,000 VF car, so 2,400 VF car. Lots of big numbers involved when you're making very heavy objects move very fast. Any questions getting from there to here? Okay. That means that since these numbers are both negative, they will add together into a bigger negative, and then we're going to divide that sum by 24,000. So the left side will become negative 252,000 divided by 24,000 equals VF car, and VF car is going to be, oops, zeros, negative 105 meters per second. Does anyone's math disagree? Yes.
Is that one down there where it says like the 90 plus, is that VF car as well?
Yes, this is 90 plus VF car. That's what we're writing instead of VF truck, as determined by our second equation with the same two unknowns.
Okay.
So we're using this equation 3 as second equation with the same two unknowns so that we can get around the fact that we don't know either of them. And the answer that we got, negative 105 meters per second, is significant for two reasons. One, it's a negative number, meaning that the car is going to get thrown backwards. It was moving in the positive direction and has now been launched very quickly in the negative direction. Secondly, it's a big negative number, so it's not just getting slightly knocked backwards, it is getting thrown backwards at very high speeds. A little over 100 meters per second is about a third of the speed of sound. The car loses this fight. It is getting knocked back, maybe not quite as fast as the eye can track, but pretty fast. It goes from 45 forwards to 105 backwards, which is a delta V of negative 150. Very big change in momentum, very big impulse for the car. Let's see how the truck fares instead. Because now that we know the car's final speed, we can bring it back over here to solve for the final speed of the truck. That would be 90 minus 150. So the truck's final speed, negative 15. It goes from negative 45 to negative 15. It slows down by 30, whereas the car's delta V is 150. The truck would notice, if it had a driver, they'd probably get whiplash. But if the sports car had a driver, they might be rendered jelly. Assuming they weren't just ejected through the windshield. Again, that's why I made these cars driverless. Questions? Yes?
Wait, can you just explain that last step? You did 90?
Oh, yes. So we determined VF car is negative 105. Gonna bring that over here to this equation, which we simplified from that third equation to get 90 plus VF car equals VF truck. So I'm gonna take that 105 for VF car, put it right there, which would be 90 minus 105 equals VF truck. Therefore, VF truck is negative 15.
Yeah, okay.
And what I'm just sort of mentally doing is I'm comparing that negative 15 to the truck's initial speed of negative 45. So it only slowed down by 30, whereas the car went from positive 45 to negative 105. So that's a delta V of negative 150 in comparison to a delta V of just 30.
And the fact that the truck continues to go at like the negative means it just keeps going in the original direction that it was going, right?
Yep, the truck is still rolling forwards from its perspective, whereas the car is turned around and thrown backwards very fast. Has this at least conceptually demonstrated why you do not want a car crash to be elastic? All right. Instead, if this was inelastic as intended, the two vehicles would move at the same velocity. They'd crumple together and probably just roll this way very slowly, which granted might be about as damaging to the truck, but the car would not get thrown backwards near as fast. It would stick with the truck rolling in this direction much more slowly. A much smaller delta V, which translates to less damage. It also translates to not getting launched away into traffic or stationary buildings. So, once again, inelastic is safer, although boring. They're also usually easier to work, because if the objects stick together, they tend to have the same final velocity, meaning we avoid the two unknowns issue. So inelastic equations are safe, boring, slower, and easier to solve, whereas elastic equations are chaotic, high speed, maintain their kinetic energy, and are oftentimes more difficult because you can't guarantee they have the same final velocity anymore. So do note that in your notes. A question on the homework or on the test will always tell you elastic or inelastic. That's not something you have to just figure out. You will be told that information. And based on that information, you'll be able to pick one or more of these equations to help you figure out final speeds in the collision. Note again, when each of these can be used. This one always works. This one works only for elastic, and it's kind of a pain. This one works only for elastic and is a little more convenient. Opinions, concerns? All right. That is the end of chapter 6. Feel good?
Yeah, what did you get for the change of velocities again?
The car's change in velocity is negative 50, as it goes from 45 forwards to negative 105 backwards. So that would be 105, negative 105 minus 45, negative 150, which I can write down actually. Sometimes it's easier to see than describe. Delta V car. It's always final minus initial. The car's final speed is 105 leftwards. Its initial speed was 45 forwards, but again, it's always final minus initial. So that's negative 105 minus 45. The car's change in velocity is negative 105. Change in velocity always translates pretty directly to size of the impulse and the amount of force involved. Definitely translates directly to acceleration. So again, the car is not having a good day. The truck, meanwhile, delta V truck, goes to negative 15 from negative 45. So that final minus initial is negative 15 minus negative 45. So the truck's change in velocity is actually positive 30, which means that it was moving forwards. Sorry, it was moving in the negative direction. It's still moving in the negative direction, just not as fast. Its acceleration pointed in the positive direction, but it's still rolling slowly in the negative direction. Despite the very large delta V's and the difference between the delta V's, the two vehicles do still share the same impulse. They still share the same impulse because two colliding objects always have equal and opposite impulses. It's just the same impulse can change your speed by different amounts depending on the mass of the object. Note that the truck has about 5 times more mass, and so its delta V is 5 times as small. 30 compared to 150, difference of 5 times. So same but opposite impulse, and that's true for every two-object collision. Questions? Anything else on your minds? All right. I do recommend looking over the Chapter 6 homework over the weekend, so that you can practice all the different types of collisions and let me know what sorts of problems on the homework are going well or possibly not going well. And we can talk about that on Monday. What I want to do now, rather than introduce a big new example, I actually want to begin Chapter 7. Because I want lab next week to be a rotation-based lab, so I want to start Chapter 7 today so that all that is making more sense by lab next week. Does that sound fair? Now when I say begin, I really do mean just begin. We're going to look at the baseline concepts that we're going to need in class on Monday, and then in lab the rest of next week. So we're just starting it. It's Friday, so I'd still like to be able to get you guys out of here early. Oh, where's my notes? Hold, please. So we're just going to dip our toes into the beginning of Chapter 7, which will be about, that's weird, rotational motion. up until this point, all of the chapters we've been looking at have involved linear motion. The word linear simply meaning of or referring to straight lines. Objects move in one or two-dimensional straight lines. They have forces acting on them that point in straight lines. All of these all these momentum vectors we've been looking at are either forwards or backwards in straight lines. The entire course up until this point has been linear straight lines up until now. And as of chapter 7, we are now going to expand our understanding to include things that don't point just in straight lines. Because it is possible, you know what? Hold please, sorry. I meant to have this prepared earlier. I forgot to grab something out of here. Because it is possible to be moving not in a straight line. Behold, is this object moving? Some people are nodding. It is definitely moving. It's not a trick. You can see that parts of it are actively in motion. But is it moving through space in a straight line? No. It is technically remaining in place. It is moving, but it's not translating one-dimensionally through space. It is still in my hands. It is rotating, which is a different type of motion. We can describe rotational motion differently to linear motion because the two can take place completely separately from one another. Objects can rotate without moving forward in a straight line, and likewise, objects can move in a straight line without rotating. In fact, we treated most objects as if they weren't rotating up until now. But even weirder is that the two can take place simultaneously as well. You can rotate and move forwards at the same time. And so, since all those types of motion can take place both separately and also together at the same time, we need to be able to define them separately and then see how they interact. So chapter 7, we're actually going to spend 2 chapters on rotational motion because there's a lot of ways that things can rotate. Everything up till now has been linear. We're now going to look at the differences between linear motion and rotational motion, while also looking at what they have in common and how they possibly overlap, because an object can move just rotationally, or just linearly, or both at the same time. So what I want to do today is define the most basic introductory terms for how rotational motion works. And as it conveniently, in my opinion, rotational motion is very similar to linear motion. The primary difference between the two is that instead of thinking of how far forwards has something moved in meters, what is the delta x or delta y, instead we think about, why did that symbol move? Oh, that's delta theta. When talking about rotational motion, the equivalent to discussing how far forwards something moves is discussing how many times the object has turned, the magnitude of rotation. The two concepts are very directly tied to each other. If an object is moving forwards, that is the direct corollary to an object that is rotating forwards in a positive direction. And we can translate how far something moved forwards directly to how many times something has spun. So, when talking about rotational motion, again, if I start spinning this wheel, you can tell that it is moving. You can see it happening. And rather than I ask you how far forwards does this object move, you could instead tell me how much does it spin. And that basically gives you the same information. It tells you the magnitude of displacement. Delta x is the linear magnitude of displacement measured in meters. Delta theta is the rotational magnitude of displacement measured in either degrees or radians. So delta theta is considered to be the rotational counterpart to delta x. They tell you the same basic information, it's just one's linear and one's rotational. And rather than measuring it in meters, it's measured in either degrees, because you can tell me how many degrees something turns. Like if I take this wheel, note where this piece of metal begins. If I grab that and bring it here, how much did it spin? 180 degrees. That is delta theta. That is the magnitude of rotational displacement. That is how far it's spun. So that's 180 degrees. A full turn is 360 degrees. You can do any subdivision thereof as well. So you guys are probably pretty used to thinking in degrees. Unfortunately, degrees is not necessarily the metric unit for delta theta. There is a different unit that our formulas are going to be designed to take more often than degrees, and that is radians. Has anyone used radians instead of degrees before? A couple people nodding. I'll admit, even in my own opinion, radians are kind of a pain. Humans are just kind of used to thinking in degrees, but radians are just another unit for it. You can convert back and forth between degrees and radians like you can between feet and meters. It's just that our formulas in this class are going to be designed to take radians instead of degrees. You're not going to have to take your calculator out of degrees mode, because we're not actually going to be using radians for any trig. So you can leave your calculator in degrees mode, you don't have to switch it. But some of our other formulas, if it has a delta theta in the formula, is going to take radians. And I will point out which ones are which. You can label them on your formula sheet if you want to. Namely, all trig equations that have a theta symbol in it, you can leave those alone. But these equations right here, in the box labeled angular, note that they have delta thetas in them instead of just theta. These are the ones I'm referring to that take radians. You may label them as such on your formula sheet. Questions about any of this information so far? All right. So, rotational motion, rather than moving delta x forwards, you can rotate some number of degrees or radians instead. And rather than calling that number of, that magnitude of rotation delta x, we call it delta theta. And it's the same theta basically as you see on a, the angle measurement on a triangle. That's why it's the same symbol again. So that's just the first variable for rotational motion. In fact, pretty much every concept that we've talked about so far that exists linearly, displacement, velocity, acceleration, force, etc. Since we're used to thinking about all those in straight lines, physics has designated rotational counterparts to all of them. Because all of those concepts that exist linearly also exist rotationally. Here we're comparing, how far you move forwards to how far something rotates in, one way or the other. Additionally, if I was to take this and make it spin, you could measure and describe to me how fast it is rotating, right? How many times it rotates per second. Does that make sense? That would be a measure of the object's rotational velocity, how fast it is rotating, how many degrees or radians it turns through every second. And if you've ever driven a car, you've seen an RPM meter that tells you rotations per minute. that is a measurement of rotational velocity. It tells you how many times it rotated per minute. So all the logic that we have for linear velocity is still true for the new concept of angular or rotational velocity. The word angular and the word rotational are synonyms, and sometimes I use them interchangeably. So if I say the word angular, I do mean rotational, and that's why the formula sheet has angular as the header for this list of formulas. So they are synonymous. Angular and rotational are synonymous. I want to make that clear. So this symbol here, this weird W, this weird villain mustache, is the symbol for rotational velocity. Rather than telling you, meters per second, how fast in a straight line, this tells you how much something rotates in 1 second. So instead of delta x, it's delta theta. It's the magnitude of rotation over time instead of distance over time. And we use a new symbol for it to distinguish it from old-fashioned linear velocity. This new symbol is technically lowercase Greek omega. Uppercase Greek omega is the upside down horseshoe. Lowercase Greek omega is this W looking thing. So for that reason, I will often say omega equals theta over t. So when I say omega, I'm referring to this. You are allowed to call it W. You can call it mustache if you want. So when something is rotating, you can talk about how fast it's rotating, and these are the symbols and formulas we use for that. This is angular velocity. How much did it rotate over time? Feel good so far? All right. Last new thing for today, last rotational concept we're going to introduce ourselves to. When I turn this wheel, you can tell me how many times it turns. That's its angular displacement, rotational displacement. You can tell me how fast it is turning. That's its rotational velocity, how many turns it goes through every second. You can also tell me the rate at which that velocity is changing, correct? Because if this was, attached to a bicycle, and initially it's sitting still, and then you begin pedaling and the wheel speeds up as the bicycle gains velocity, the rotational velocity of the wheel does change through that process, right? Initially it's not rotating, and then it starts rotating. That is a change in its angular velocity, in its rotational velocity, correct? So, that means that rotational velocity can change, like how linear velocity can change, which means that there is also such a thing as rotational or angular acceleration. Linearly, we've got A equals change in velocity over time. Rotationally, we have rotational acceleration equals the change in rotational velocity over time. Same basic logic, it's still a change in the speed over time, it's just instead of meters per second forwards, it's radians per second turning. So an angular acceleration would be, or rotational acceleration, would be if you were driving and you hit the gas and you see not just your speedometer, but your RPM gauge increasing. Because that's a change in the rotations per minute. That's a change in how fast the rotating bits of your engine are moving. And the symbol for rotational acceleration, it's technically not lowercase English a. This is technically lowercase Greek alpha. Because there's definitely a huge difference between those two symbols, right? I don't know who decided to use this. I mean, it kind of makes sense to keep using A, but depending on the font, it's not a huge difference. So whenever I write this character by hand, I tend to overemphasize the difference between them. When I write A, it just has a lower tail. When I write alpha, I overemphasize the upper tail. And I do something like this. Oops. I make it look like a fish. In fact, I think technically the Jesus fish is lowercase alpha. Please correct me on that if I'm wrong. At least I think it's based on alpha. Anyway, so when I'm writing it by hand, I overemphasize this upper tail, which is the only real difference between script alpha and script A. If I'm reading this formula out loud, I would say alpha equals delta omega over delta t. You may call it fish if you really want to. Fish equals W over T. Fish equals mustache over T. Whatever helps you keep everything straight in your head. Feel free to also, on your formula sheet, turn all the A's into fishes if it makes it easier to tell the difference between A and alpha that way. So these three rotational variables correlate directly to the first three linear variables we learned about: displacement, velocity, acceleration. All the same movement logic we've been using works in the rotational world. We just have to use radians instead of meters, because we're talking about, you know, how far something has turned rather than how far it has moved in a straight line. And we use different symbols for the rotational ones to distinguish them from the linear ones. But all the same logic still applies. All these formulas so far have directly matched their old linear counterparts. And that actually continues for pretty much every single formula we've used in this class. Every formula we've used that involves linear motion, say for instance, the first four formulas, all the logic here that relates to linear motion is still true for rotational motion. You just replace all the English with Greek. Notice how these angular rotational formulas are exactly the same as the old linear ones. They just replaced all the symbols. All the logic between the concepts is the same. Velocity is still displacement over time. Acceleration is still change in velocity over time. If you're accelerating, you're still displacing over time. And as you displace while accelerating, your velocity changes. Same formulas, and that's why they are organized opposite each other on your formula sheet. You'll notice the first four formulas here have been labeled linear since the beginning of the term, and directly opposite it is a box that says angular, meaning rotational, that lays out the same formulas in the same order, just using the Greek instead of the English. So what we're going to be spending next week doing is looking at how all of these rotational concepts work and how they are basically the same as the linear ones. We're just using radians instead of meters. As an introduction to the concept, how's this feel? Okay. We're not throwing anything out the window. Linear motion still exists and all that logic still applies. We're just expanding our options for describing motion. So now we can do rotating and moving linearly. So, any questions before we break for the weekend? All right. Do look over chapter 6 homework. Let me know any questions you have while working on that. And come prepared next week for things to start spinning. Have a great day. Stay dry. Oh, I'll put it back. Oh, no. Honestly, one of my students here just stopped taking notes, so it's fine. So this is technically an explosion, like the cannonball, the rocket launcher that we did. Initially, the person in the oxygen tank start together at rest.